So yesterday we have seen the introduction of data protection concept. Okay. So in this particular architecture, we have different levels of data protection required. Okay. One is at the disk level, which we have seen yesterday. Okay. The concept used at the disk level to give the data protection is called as the RAID, the redundant array of independent disks. Okay. Within the RAID, we have two sub-concepts, RAID 1 and RAID 5, where RAID 1 is a complete mirroring of the data, where RAID 5 is a parity is stored in the mirror disk so that they may rebuild the data 100% in the time of disk failures. Okay, so the RAID 1 is completely reliable because the whole data is copied on the mirror disk, so you can get back the data definitely even in case of a disk failure. But in RAID 5, we may have a risk that we may not be able to build the data. Okay. So we have the next level of data production required at the AMP level. Okay, so first is at the disk level we have seen yesterday, and now we are going to see the AMP level data production. And in the architecture, the next components are BINET, where they itself has the redundant BINETs. So it was already the fault tolerance techniques, and P is the parsing engine, which is the thinking process. Okay, so data production is not required at the PE level, because if PE is down, some other PE can handle the AMPs which are handled by this PE. Okay, so dynamically it can be taken care. So we have the next component level called node level. So if an entire node failed, then how you can get the data back? Okay, so these are the three levels of data production we'll see, and then later we'll see the transaction level production and the object level protection. Okay, so first one is the disk level, which we have seen yesterday, and the AMP level, and the next one is the node level, and then object level and the transaction level. So these are the protection levels we are going to cover. Okay, so today we are going to see the AMP level data protection. Okay, so here let us consider there are 4 AMPs. Okay, and these 4 AMPs has data aligned to them in the primary rows, if you see. Okay. And to have a data protection at the AMP level, they group a certain number of AMPs called as a cluster. Okay, so in the configuration of, let's suppose I have 16 AMP system. Okay, in the 16 AMP system, I have grouped each 4 AMPs as a cluster. Okay, so in my cluster I have 4 AMPs, AMP0, AMP1, and AMP2 and AMP3. Okay, so what happens if I join the AMPs as a cluster? So if I join a cluster and if I protect data with the fallback, then each and every row which is stored in the primary section of the AMP will be stored as a fallback in other AMP within the same cluster. Okay, so let's see, we have a record 62 here. It is stored in this AMP0 as a primary row. Okay, so this particular row is stored as fallback in other AMP within the same cluster as fallback row. Okay, so each AMP will have 2 sections, primary rows and the fallback rows. Okay, fallback is nothing but the backup of the data which may be residing as a primary data in the other AMP within the same cluster. Okay, so there are 2 definitions we have to understand. First one is the cluster. What is the cluster? Cluster is the group of AMPs in which the fallback data is shared. What is a fallback? Fallback is the backup of the row which is stored within the cluster in other AMP. Okay, so these are these 2 recursive definitions we have to understand. Okay, first, what is the cluster? Cluster is the group of AMPs in which the fallback data is stored. And what is fallback? Fallback is the backup of the row which is stored in the fallback section of the other AMP within the same cluster. Okay, so what happens with this arrangement? What is the benefit we are going to get out of this arrangement of cluster and with fallbacks? Okay, let's suppose in case of an AMP0 failed, then can I still access my data? Yes, because the 60D is stored as fallback in the AMP2 and 8 has stored in fallback in AMP1 and 27 is stored in AMP3 as fallback. So I can still retrieve all my data out of the other AMPs within the same cluster. So there is no problem for me even though one AMP failed in the cluster. Okay. A fallback cluster is defined a set of AMPs across which fallback is implemented, and all fallback rows for AMPs in a cluster must reside within the cluster. The loss of one AMP in the cluster permits continued table access. Okay, even though one AMP failed, I can still continue accessing my table. Loss of two AMPs in the same cluster cause the RDBMS to halt. Okay, so if there are two AMPs failed within the cluster at the same time, then we may lose our data. So we cannot retrieve all the data of the tables. So we have to halt the RDBMS in such a case. But we will see what is the probability of failure of two AMPs within the same cluster at the same time. Okay, we'll see that because we already have the data level production at the disk level and we have at the AMP level. So with the combination of the RAID and with the combination of the cluster fallback, data is highly protected. So there is very less probability of failure of two AMPs within the same cluster. We will see that with an example. Okay. Let's suppose if one AMP failed, okay, I can still be accessing data from other AMPs where the data is stored in the fallback section of other AMPs within the same cluster. And now during the failure of AMP0, I'm trying to update data of the AMP0 in the fallback section of the other AMPs within the cluster. Let's suppose 62 is here. I'm trying to update the row of 62 with some new information during the absence of AMP0. Okay, I have updated it here. And now AMP0 came back after repair. It came back in active status. Then how it would get all the new status of the records into its primaries and into its backups, fallbacks. Okay, during its absence, some updates might have happened on the data. So how it will get the updated data back? Okay, so what happens whenever an AMP failed, all other active AMPs would start noting down all the transactions which would happen on the failed AMP's data. Okay, that process is called down AMP recovery journal. Okay, during the absence of one AMP, all other AMPs would start writing all the transactions that may happen on the failed AMP's data into a journal called down AMP recovery journal. Okay, so all AMPs start that. Whatever transactions happen on its primary data or in its fallback data, they will start noting down in the journal called down AMP recovery journal. Okay, and once this AMP0 got repaired and get back into an active status, it will read the journals which was written by all other active AMPs during its absence, and then it will try to make all the transactions on their own data so that the data will be in sync with the fallback section of the other AMPs or the primary section of other AMPs for the fallback information, so that all the data here would be updated and made in sync with all other AMPs fallback data or the primary data, whichever it contains. Okay, so this is the technique used in case of an AMP failure. The technique used is fallback cluster, so that the data is stored in the fallback section of all other AMPs within the same cluster. So in case of an AMP failure, you can still access the data, and whatever updates happen on the data during the absence of the AMP, they will be stored in a journal called down AMP recovery journal. And this journal will be read after AMP came into the active status, and it will make the data in sync with the all other AMPs, so that we'll have all updated data in all the AMPs. Okay, this is called as amp level data production fallback clusters. Okay, so now we will see the combination of the RAID 1 and the fallback cluster, okay, how much efficiently they were aligned to give us maximum data production. Okay, so in this example we'll see the RAID 1 with a fallback combination. Okay, we have a cluster here with a combination of 4 amps, amp0, amp1, amp2 and amp3, and we have the primary data stored, and we have the corresponding fallback data also stored within the cluster in other amps. Okay. And the data which is stored on the amp actually stored on the virtual disk, right? So whatever data, when I say amp is stored, the data is actually stored on the corresponding associated virtual disk. And here at the disk level we have the RAID 1 production, there is mirroring of the information. Okay, so whatever amps data is there, the amp data is stored in the primary disk and the mirror disk also. Okay, in the primary disk it stores the primary information and the fallback information, and the same data is mirrored in the mirror disk also. Okay, it happens in all the amps similarly. Okay, now let us see if one amp or one disk failed here. In the amp 0 the primary disk failed. Okay, when it failed, can I access the data? Yes, because I have the mirror disk available, so I can still access the data. Okay, amp is not down, but the primary disk of the amp 0 failed. As the mirror is still active, I can access the data. Okay. At the same time, let's suppose one more disk failed in the same cluster. Okay, so what is the possibility that two disks fail within the same cluster at the same time? Okay, the probability is less, because two disks, because all the disks are independent. Okay, it is not that one disk failed so the other disk is also failed. All disks are independent. Okay, there is less probability that two disks within a same cluster failed at the same time. Let's suppose it is also failed, two disks failed, but still can I access the data in this case? Yes, here the mirror is available and here also the mirror is available, so I can still access my data. Okay. And now let's suppose the mirror disk in amp 0 also failed at the same time. Okay, so the primary disk failed here, in amp 2 also the primary disk failed, and at the same time let's suppose the mirror disk in amp 0 also failed. So what happens if two disks fail within a single amp? Okay, the primary disk failed and mirror disk failed, so we will say the amp also failed, because this amp cannot get data from any of the disks, so the amp failed. Okay, so if the amp failed, can I get the data back? Yes, I have the data production implemented at the amp level called fallback cluster, so I can still retrieve my data from the fallback sections of other amps within the cluster. Okay, so 62 can be accessed from here, or 8 can be accessed from here, 27 can be accessed from here, so I can still able to access my data even though one amp failed. Okay, so by now we have seen 3 disks failed within the same cluster at the same time. Okay, and now let's suppose one other disk failed somewhere. Okay, as mirror is available, we still can access the data. Again, what is the probability that 2 amps fail? Okay, in order to fail one more amp, the 2 disks within that particular amp should also fail. Okay, in amp 2 the primary disk failed, so at the same time if mirror disk also failed, that means totally 4 disks, and the 2 within the same ranks or same amps should fail at the same time in order to have 2 amps failure within the cluster at the same time. Okay, so what is the probability of having 4 disks failures? Get that 2 within the single amps at the same time. Okay, it is very less. right? So we can say the data is very much highly protected, okay, with the help of the RAID 1 and the fallback protection what we provide in Teradata. Okay, so this is the capability of Teradata at the disk level and at the AMP level, and with the combination it is highly protected. Okay, and after this we have a node level failure or fault tolerance technique. So even though 2 amps failed here, okay, we can still access the data with the node level failure technique, which we are going to see soon. Okay, so even though one disk failed or 2 amps failed or one node itself failed, we can still access our data in Teradata. Okay. So the technique which we call at node level is called as a click. Okay, before going to the click, let me see if you all have any questions. Any questions?
Manohar, Pavan here. I have one question.
Yeah.
So, how is the distribution of data on the fallback cluster decided? Like, how is data hashed to the fallback? So,
Yeah.
how will basically optimizer know to which fallback cluster data has to go to?
Yeah. So whenever we put a fallback keyword at the time of table creation, okay, the hash algorithm would identify the primary amp in which it has to be stored and the fallback row also. Okay, so fallback is under control of the developers, okay, where they can have the keyword fallback at the time of table creation, so that the algorithm will know that this row to be stored in 2 amps. Okay, so it will identify which is the primary amp and which is the fallback amp.
Okay.
Okay, so as we observe, the fallback is also a 50% of data storage overhead. Okay, so we have to carefully choose whether this data in the table should be protected with the fallback or not, because if we give a fallback, it will occupy almost 100% data, I mean 100% space more. So it is under control of the developer. We have to carefully analyze it, because it is a burden at the time of insertion, because the hash algorithm has to identify 2 amps to store this data. Just a moment. Okay. So it has to identify 2 amps. One is the primary amp and one is the fallback amps during the insertion of the data, and it occupies 100% of more data. Okay, so we have to carefully choose whether a fallback is really required for this table or not. Okay, generally we go for fallback for target model tables, which will be accessed continuously by the report tables. Okay, we don't put fallback for the staging tables or for the temporary purpose tables, okay, work tables, okay, all those things, all those tables we don't really put fallback, but we prefer to have fallback to the target model tables. Clear? Okay, so let's go with next level production. Click. Okay. So click also the similar technique of cluster, where they group a number of nodes as a click. Okay, the spelling is CLIQUE and it is spelled as click. Okay, so click is a set of SMPs, that means nodes, okay, that share a common set of disk arrays or a common set of memory pool. Okay, so here we have the memory, and in the configuration, let's suppose we have some 16 amps, and within the 16 amps these 4 nodes are sharing the common pool of memory. Again, these 4 nodes are called as a click. A click is a group of nodes which are accessing a common pool of memory. Okay, if you observe, each and every node has redundant connection with all the memory. Okay, if you see here, we have binet 0 and binet 1 here. blue and green, and each has the connectivity with all the memory. Okay, each connection within the node has all the connectivity with all the memory. Okay, if you see SMP001, we have red lines and black lines, binary 0 and binary 1. So with this, okay, it has connectivity to all the memory of the system. Okay, similarly, SMP1, SMP11 and SMP12. Okay, all the nodes are sharing a common pool of memory here. Okay, so this arrangement where a group of nodes sharing a common pool of memory with these redundant binaries are called as a clique. Okay, so what is the advantage we are going to get with this arrangement of clique? Okay, in the clique, let's suppose one of the node failed. Okay, one of the node failed. So automatically all the virtual processors which are running in this particular SMP would migrate to all other active nodes at that time. Okay, a reboot is required. Okay, once the SMP failed, a reboot is required, and with the reboot, all the virtual processors would migrate to all the active nodes by the time in the click. Okay, so that all the nodes will have some more burden, but still we can continue accessing the data. Okay, maybe performance degraded at 1/3, because out of 4, if one is failed and the all other nodes are sharing its burden, so 1/3 of the performance may be degraded, but still we can continue accessing the data. Okay, when actually a node fails, when 2 amps are down, right? So what is the probability of having 2 amps fail? It is very less, because the 4 disks, and that too within the same disk, the main disk and mirror disk has to fail. So the probability of having 2 amps failed in the cluster is very much rare. Okay, and then we say the node is failed. Okay, at the node failure also we have the fault tolerance technique called clique, where the virtual processors of the failed node are migrated to all other active nodes. Okay, so all other active nodes will have a burden. So one third of the performance is degraded. Okay, so this is called as a clique. Okay, so within the clique, if we do not want to lose our performance, okay, then they may go with a configuration called hot standby node cliques. Okay, within the cliques, they will have one node which sits idle, okay, and it is called as hot standby node, because so it is a backup of the nodes which would stay in the clique without doing anything. Okay, in case of failure of any of the node, automatically the virtual processors which are running in this node will be migrated to the hot standby node. Okay, all the virtual processors would migrate to the hot standby node. No reboot is required. Okay, whenever the failure happens here, okay, there is no distribution, right? So the no reboot is required. All the virtual processors would directly migrate to the hot standby node, and the data can be still accessed with the same performance without a reboot. So this configuration is a bit costly, because we have to have a idle node sitting without doing anything. It waits for the node failure within that clique, and if any node fails within the clique, then automatically the virtual processors will migrate to the hot standby node and will continue accessing the data. Okay, so this is a clique here in this diagram, and this is a clique. Okay, you can see a hot standby node which doesn't have anything, any virtual processor are not doing anything. In case it fails, in case suppose node 5 fails, all the processors would migrate to node 8 and will still continue accessing the data. Okay, so performance degradation is 0%, because earlier also 3 nodes are running and now also 3 nodes are running, so there is no performance degradation. Okay, but when node 1 is recovered, it becomes the hot standby node. Okay, when node 1 comes back after repair, it would act as an hot standby node, and these are working continuously. Okay. So in earlier state, when SMP failed, we have to reboot the system. So the virtual process will be distributed, and when this SMP comes back after repair, then again a reboot is required, so that all virtual processors will be distributed across all the nodes within the click. Okay, so in this type of configuration where we don't have a hot standby node, we need to have two reboots in case of a node failure, but still we can continue accessing the data with a lesser performance. Okay, so if organizations are not expecting any data degradation, any performance degradation in case of a node failure also, okay, the Teradata will prefer to have a hard standby node configuration where it is costlier because they are keeping a node extra in the configurations. Okay, but here the advantage is there is no restart or reboot required in case of a node failure or in case of the node coming back into active status, and there is no performance degradation. Okay, so this is all at the time of configuration. Okay, the high level executives have to take decisions. The high level architects, okay, or DBS would take decision, okay, how much performance they want for their system and how much cost they can put on their configuration of the nodes. Okay, so this is called as hot standby node, where we'll give 100% of performance even in case of a node failure, and no outage is required even a node failed or it came back after the repair. Okay, this concept is called as a click. Okay, so let's move ahead for the other topic called data integrity protection. Okay, so this is a object level protection, we can say. Okay, because in the multi-user environment, okay, multiple users are working on same components at the same time. Okay, let's suppose if we all are working on the same application, okay, we may all access the same databases and same tables, same views, okay, same objects at the same time, right? So in that multi-user environment, we need to have a proper environment where we can have the object integrity retained, right? So let's suppose if I am updating a data, if some other user is reading the data at the same time, he may not get updated information. Okay, so the RDBMS should not allow other users when a user is writing the data on it. Okay, so we have to have some locking mechanism so that when a user is writing the data, no other user can access this object. Okay, so to have the object level protection in the multi-user environment, we need to have a concept of locks. Locks is a general concept in all the RDBMS. Okay, similarly, Teradata also has the locks concept. Okay, we are going to see what type of locks and how we can modify the default locks and what level of locks we can have. What are the default locks obtained when we fire a query? Okay, all these things we are going to see in this chapter, locks. Okay. In Teradata, we have basically 4 types of locks. Okay, let's start with read lock first. Okay. Read lock. If I try to read the information, that means select the information, then a default lock obtained on the object is called as a read lock. Okay. So when I obtain a read lock, no other user can write the information at the same time, right? Because I'm reading it, I'm expecting that I'm reading an updated information, and if some other user is updating it at the same time, okay, so I may lose my data integrity. I may get some old data, I may get some new data, so the data integrity is lost. So during I read the table, I don't want any other user to write the information at the same time. Okay, so read and write are not compatible. When I have a read lock on the object, no other user can obtain a write lock. But how about another read lock? Okay, I am reading the data, and another user also wanted to read the data at the same time. Can I allow him? Because I'm reading the data and he also wanted to read the data. Okay, as both are read operations, we can allow that. Right? So read and read are compatible. If I'm obtained a read lock and if any other user at the same time wanted a read lock on the object, we can allow him. Okay? But read and write are not optable. Okay, not compatible. And what about write? If any user obtained a write lock on the object, so he's updating some information in the table. Okay. No other user are allowed to read the data at the same time because read and write are non-compatible, which we already know. So when a object is locked with write, where he is updating the data, he won't allow any other user to read the data. And how about write? Okay, I'm writing the data on the table and any other user also wanted to write the information on the table at the same time. Can I allow him? No, right? Because I am updating the data and he also wanted to update the data. Okay, there may be a collision in the updates. I may lose my updates or he may lose his updates if I allow both of them to write the data on the same time on the same table. Right? So the write and write is not compatible. Okay. Here read and read is compatible, but read and write is not compatible. But with write and write is also not compatible. Anyway, read is not compatible. Okay. Now I have a scenario where I am trying to generate a report, a historical trending report on a table which has some millions of information. Okay, I have some 20 millions of data on the table and I am trying to generate a trending report on the historical information of 10 years, let's suppose. Okay, from 2000 onwards till 2010, I just wanted to generate a trending report how the sales was. Okay, and at the same time, the ETL developers or the batch operations, the ETL batch operations update the current month information for the current day. Okay, the batch process which runs every day, it is updating the current table, the same table for the current month, current day. Okay, and my report is generating a trending report for the last 10 years, the historical information. Okay, and I have obtained the lock as a read. Yeah, as I'm generating the report, I have obtained a read lock, and it has to access all the 10 years of data, which is more millions. So I may take much time to generate that report. Okay, and this current batch process with the write operation, which is required to update only the current month's information, okay, which is maybe 10 to 20 records, let's suppose. The write operation requires only 10 to 20 records to be updated for the current day information, and I'm generating some trending report out of some millions of data. Okay, so this write operation has to wait till my report generation completes, right? Because I have obtained the read log, I'm accessing the millions of data to generate the report. It may take much time, where this batch operation, the write operation, may take very lesser time to update only 10 to 20 records in the table. But still it has to wait because the read and write is not compatible. Right? So what is the solution for it? Unnecessarily the write operation is waiting till the read completion. Okay, even though he writes the 10 records for a single day, it may not impact my report, which is of 10 years of trending. Right? So it won't impact me much on a trending report of 10 years because they are updating only one day information in it. Okay, so in this scenario, we are indefinitely waiting. The batch operations are indefinitely waiting till the completion of the read operation. So is there any solution for it? Yes. Okay, that is called as an access lock. Okay, so instead of locking the object for the read purpose during my report generation, if I would have locked with the access lock, I can allow other users also to write the data on the same table at the same time. Okay, that is called as an access lock, where it is compatible with reads or with writes and with access itself. Okay, if there is a need where you are generating a high volume of data reports, but you don't want to lock any other objects which are writing the data on the object, then you may lock the object for access purpose. Okay, if you access, okay, if you lock the object with an access lock, then all other users can write the data also on the same table at the same time. That is called as an access lock. Okay, but there is a possibility that you may get some older information or some old data or which is not updated information. So this lock is also called as a dirty lock, because we may get some dirty data which is not update as of now. Okay, so access lock is also called as an dirty lock, where it will allow other users to write the data also at the same time while reading the data or accessing the data. Okay, that is called as an access lock. So access is compatible with read locks, access is compatible with write locks, and access is compatible with access itself. If two users wanted to lock the object for access purpose, they can do it. If any other user wanted to have a read lock on the same time, yes, he can have it. If any other user requested write lock on the object, yes, he can have it. Okay, so these are called as access lock and called as a dirty lock also. And now we have one more lock called exclusive. As its name indicates, it is dedicatedly for those users who obtain the exclusive access. Okay, so once a table is locked with an exclusive lock, no other user can obtain any type of lock on the object till the completion of the exclusive lock. Okay, so suppose if I am altering a table by adding a column or by changing its data type, or if I am creating the table, during the creation of the table or during the altering of the table structures, the table should not be accessed for any of the purpose, even it is read or even it is access, even it is write. Okay, so in such situations, okay, the default lock obtained on the object is exclusive lock, where any other user can obtain any type of access. Okay, so it is a highly restrictive lock which is not compatible with any of the locks, even with exclusive itself. Right, so exclusive is not compatible with access, read, write, and exclusive itself. If exclusive is obtained, no other lock can be obtained. If any other lock is there, exclusive cannot be obtained. Okay, it is restrictive in both the sides. It is highly restrictive lock where it won't allow any other user to obtain any of the lock on the object at the same time. Because these are the 4 locks in Teradata. Okay, and all these locks can be obtained at database level. You can directly lock a database, or within the database a table can also be locked by any of the locks, a table or a view, or a group of rows which are having same row hash value can also be locked as a group. Okay, so these are 3 levels of locking you can obtain in Teradata. At the database level you can lock the object, at the table or view level you can lock the object, or at a row hash level. At row hash level is nothing but the rows which have same row hash values can be locked together. Okay, for example, if it is a non-unique primary index, the primary index can be duplicated, so we may have same row hash value generated for all the rows which has the same primary index. So all these rows as a group can be locked as a row hash level lock. Okay, so these are 3 levels of locking in Teradata. Okay, and then these are the default locks obtained whenever you execute a DML, DCL, any of the queries. Okay, if you write a select query on the object, the default lock obtained is read lock. Okay, if you do an update or insert, then it would be a write lock. Okay, if you do a create table or alter table, then it would be an exclusive lock. So these are the default locks obtained. Okay, we can modify the lock to be obtained on the object with a statement called locking modifier. Okay, so these are the default locks, but while select the operation on the table, you don't want to lock it for read, but you want to lock the object for access lock so that other users can also write the data at the same time. So how we can do that? We can change the default lock with a statement called locking modifier. Okay, this statement. Okay, we have a locking modifier statement with which we can degrade or upgrade our locks during our access on the objects. Okay, see now, I have written a statement locking row for access. So what level of lock I require? A row level lock on the table for the access purpose. That is access lock. Okay, so this is called as a locking modifier statement. Locking row for access and then my actual SQL. Select star from table A. If I don't give this locking modifier and I do a select star from table, default lock obtained is read lock on the table A at the table level. Okay, so now I have modified my lock at the row level and with an access lock, and it follows the regular query. Select star from table. Okay. Other example, locking table B for exclusive, and then I'm doing my update statement. Generally, if I do an update, a write lock will be obtained on the object. But if I want to change the lock to exclusive, so exclusive means highly restrictive so that no other user can read or write or can access the data. Okay, so I have obtained an exclusive lock before I do an update. Okay, if there is any scenario where you want to restrict all other users during your update, you can upgrade your lock to exclusive and you can do your operation with your normal query. Okay. And here this table will give you the summary of compatibility of the locks. Okay. So how to read this table? First see what lock is obtained on the object. So it is none. And what is the lock request coming in? It is an access lock, and if there is no lock on the current object, can we grant it or not? Yes, we can grant it. Okay, and if there is no access, if there is no lock on the object and a new read request is coming in, can we grant it or not? Yes, we can grant it. Okay, like that. Okay, the write and exclusive can be granted if there is no lock on the object. Let's suppose a table is locked by access. That is an access lock on the object. Then a new access request is coming in on the same object at the same time. Can we grant it or not? Yes, we can grant it because access and access is compatible. Okay, and incoming request is read during the object is already locked by access. So can we grant it? Yes, because access and read is compatible. Okay. And how about write and access? Yes, they are also compatible. So newly incoming write lock is also be obtained on the object because the object is already locked by access, which is compatible. But a exclusive lock is coming in as a new request. Can we grant it? No, because exclusive is highly restrictive, which cannot be obtained if any other lock is already placed on the object. So we cannot grant it. So it has to be waiting in a queue. Yes, after the completion of access only we can grant this exclusive. And similarly, if a object is locked by read, can we grant access? Yes, we can grant it. Can we grant read? Yes, because read and read are compatible. Can we grant a write? No, write and read are not compatible. So The write has to be wait in a queue. How about exclusive? Exclusive is always be queued, right? So how about the object is already locked by write? The only access lock can be granted because access and write are compatible. But write is not compatible with any other locks. So all other incoming locks should be waited in a queue. And if it is an exclusive lock which is already obtained on the object, then every incoming lock request should wait in a queue. Any one of the lock can be not granted when the object is already locked by exclusive lock. Okay. And here in this example 1, we'll see what types of queues are there. Okay, let's suppose current lock on the object is read. Okay, and a write lock is coming in as a new request. Can I grant it? No, because read and write are not compatible, so I cannot grant a write lock on the object. Okay, and at the same time one more incoming request is also coming in as read. Okay, so read is compatible with read. Can I grant it? I would have granted, but a write request is already there, right? So the first come first serve basis. Okay, the current lock is read. A first request came for write purpose, and the second request come for read purpose. Even though this read is compatible with read, I cannot grant it because the first come first serve basis, the write lock to be obtained first. So both these two locks which are coming new has to be wait in a sequential queue. Okay, the current lock is read. The write and read should be waited in a queue. It is called as a sequential queue. Okay, even though the read is compatible with read, I cannot grant it because the write is already there, which is in the queue. Okay, so after this read completes, the write will be obtained, and then after write completes, then only this particular read will be obtained. Yeah, this is a sequential queue. Yeah, let's see second example where the current lock is write and the newly incoming request is read. Can I grant it? No, because these two are not compatible, so it has to wait in a queue. And at the same time, one more read request is coming in. Can I grant it? No, because it also has to wait in a queue. And in the queue, these two reads will wait in a parallel queue because in the queue, the requested locks are compatible. The read and read are compatible. So these two will be waiting in a parallel queue. So whenever this write completes, both the reads can be obtained at the same time. Okay, so it is called as a parallel queue where these two locks are compatible. They will wait in parallel. So once the write lock, the current lock is completed, both the read requests can be obtained at the same time. Okay, so this is all about the locking mechanism in Teradata. Okay, so let me open the lines so that you can come up with your questions. Any questions?
Manohar, Pawan here. So this locking, does it vary by level of access also?
Pardon?
I mean the compatibility. Will the compatibility depend on the level of access? Let's say I'm only reading a certain set of rows. Can somebody gain exclusive access to some other set of rows?
Yeah, if exclusive on the other set of row level, then it can be granted. But if they obtain, if they are requesting for at a table level, they cannot.
Okay.
Any other questions? Okay. So tomorrow we'll see the next level of production called transaction level. We will see the journals. Okay, so tomorrow we'll meet at the same time and we'll continue the data production concepts.